Okay, we are online.
Okay, thank you, Julian. I would like to introduce our next speaker of today. It's Professor Igor Grzelec, also from AGH University in Kraków. And Professor Grzelec is going to give a talk entitled On a New Problem About the Local Irregularity of a Graphs. So please, Igor, it's your time.
Okay, so I will be talking about a new problem on the local irregularity of graphs. This is a joint work with Tomasz Madaras, Alfred Onderko, and Roman Sotak, and our results comes from two my stays in Košice this year. So I will start with some basic definition. So we say that a graph is locally irregular if any two adjacent vertices have different degrees. This graph is locally irregular, and the second is not, because we have two vertices with the same degree, and this degree is equal to 2. I will be talking about edge coloring of a graph. So by edge coloring of a graph, we mean an assignment of positive integers from 1 to k to the set of edges of a graph. And it's worth to mention that the edge coloring of a graph is not always proper. And two more definitions which will be useful. So we say that an edge coloring of a graph distinguishes neighboring vertices of the graph by sums if each two neighboring vertices have different sums of colors of incident edges. And the corresponding parameter, so the smallest number for which such coloring exists, is called general neighbor distinguishing index by sums. And the second definition is a definition of the local irregular edge coloring of a graph. So we say that an edge coloring of a graph is locally irregular if each color induces a locally irregular subgraph. And the parameter is locally irregular chromatic index. Here we have three simple examples of locally irregular coloring of path of length 6 and two cycles. The coloring of this cycle and paths like this will be very useful to solve our problem. Our problem is closely related to two well-known problems. The first is Tutu conjecture, and the second will be local irregularity conjecture. So the Tutu conjecture was proposed by Bordeaux and all co-authors in 2019 and says that every connected graph of order at least 4 has a Tutu coloring. By such a coloring, we mean a decomposition of a graph into at most two subgraphs, such that in each of these subgraphs, neighboring vertices can be distinguished by sums using at most two colors. We can also formulate the Tutu conjecture using the language of multigraphs, and in this notation we can say that every connected graph G of order n greater or equal to 4 can be distinguished, can be decomposed into two subgraphs, red subgraph GR and blue subgraph GB, such that there exist locally irregular multigraphs G hat R from the family of all multigraphs which have edges with multiplicity at most 2, and blue submultigraph from the family M2. So from GB, so the family of multigraphs created from a graph GB, where the edge multiplicity is at most 2. This simple example shows that 2-2 conjecture holds for a complete graph on all vertices, and obviously it is worth to mention that 2-2 conjecture is now still open, but we have some partial results about it. The first was obtained by Bodo and CaRT in 2019, and they confirmed the 2-2 conjecture for non-locally irregular graphs, complete graphs, bipartite graphs, degenerate graphs, and subcubic graphs. 2 years later, more general result was obtained by Przybyło, and he proved that for every graph of minimum degree at least 10 to the power of 6, 2-2 conjecture holds. The second conjecture connected with our problem is local irregularity conjecture, which was proposed in 2015 in this version, because now, as I tell a bit later, we know a bit different version. The first version says that if a graph is decomposable, then we can find such a decomposition into at most 3 locally irregular graphs. But obviously not all graphs are decomposable into locally irregular graphs. For example, paths of odd length, cycles of odd length. Also the family F. And family F together with odd length paths and odd length cycles we denote by family F prime. So now I will introduce the definition of family F. So it's defined recursively in the following way. We start with a triangle, then we add to this triangle even length path, and we add to this triangle even length path the vertex of degree 2 on triangle, and to this family also belongs graphs which are obtained from graphs from family F by adding odd length path ended with triangle, and we can join such such elements to the vertex of degree 2 on triangle. And we continue adding odd length paths ended with triangle and even length paths to vertices of degree 2. And only the family F prime is the family of non-decomposable graphs. Every other has decomposition into locally irregular graphs. Obviously, we also know the constant upper bound of the local irregular chromatic index if the graph is decomposable. So it was obtained in 2017, and this bound was at the time 328, and 1 year later it was lowered to 220. Also, the local irregularity conjecture was conferred from some classes of graphs, among others paths of even length, cycles of even length, complete graphs, trees, hypercubes. Almost all CaRT, by almost I mean all except one particular, decomposable subcubic free graphs, the regular graphs where d is greater or equal to 10 to the power of 7, and graphs of minimum degree at least 10 to the power of 10. Moreover, we have also some constant upper bound for some classes of graphs, among others subcavic graphs. The upper bound is 4, and for planar graphs, obviously, which is decomposable, the upper bound is 15. But as I suggested a moment ago, there is one CaRT for which the local irregularity conjecture does not hold, and it is shown here. This CaRT graph requires 4 colors for locally irregular coloring, and this graph was the reason why Mr. Szklarkowski and Ilana Sedlar proposed a new version of this conjecture after examining the whole family of CaRT. And they proposed that this CaRT is the only counterexample for the initial version of the local irregularity conjecture. The second problem related to our problem is the local irregularity conjecture for two multigraphs, which says that for every connected graph, which is not isomorphic to path of length 1, multigraph 2G obtained from G by doubling each edge has local irregularity chromatic index less or equal to 2. And this multigraph 2K2 is the only non-locally irregular colorable to multigraph. And here we have some simple examples. We confirm this local irregularity conjecture for two multigraphs for paths, cycles, wheels, complete graphs, complete k-partite graphs, bipartite graphs, CaRT, and split graphs. Obviously, we should note that this conjecture is independent from Tutu conjecture because in the Tutu conjecture we do not allow multi-edges colored both colors, but such edges are allowed in the coloring of two multigraphs. So we have local irregularity coloring of multicycle 2C3 as it's presented here, but we cannot find locally irregular coloring of cycle C3 even if we multiply some edges in one color. From our theorem, which I presented a moment ago, we can easily see that local irregularity conjecture for two multigraphs holds also for graphs from the family F prime, except from multigraph 2K2. We also proved some general upper bounds. So for planar graph, which is connected, the upper bound is 4, obviously except for planar graph, which is a path of length 1, and for every connected graph, which is not isomorphic to path of length 1, the local irregularity conjecture for multigraph 2G is less or equal to 76. We obviously believe that the bound will be lower, but we cannot prove it now. And during my stay, we proposed a new problem. So let G be a connected graph, which is not isomorphic to K2 or K3, so path of length 1 or a triangle. And the question is, what is the minimum number of doublet edges required in the multigraph G hat obtained from G if we would like to find a local irregular edge coloring of G hat with at most two colors, and we do not allow multi-edges colored both colors. So in fact, this question is the question of minimal number of double edges used in the coloring proposed by Tutu conjecture. So this problem is harder than to conjecture. The corresponding parameters on the minimum number of required double edges will denote by the layer of G, and we can easily see that our problem has a solution if and only if Tutu conjecture holds for a graph G. And the second thing is that if the locally irregular chromatic index of a graph G is less or equal to 2, then we don't need to multiply any edges. For better see what happens in our problem, I provided some simple example. So if we consider path of length 5, we can easily see that if we multiply first edge and color the first 3 edges by one color, then we create here locally irregular graph. And the remaining 2 edges we color in the other color, and we have locally irregular coloring of a path of even length or of odd length, and this coloring could be easily extended for longer paths. In case of cycles, we have to start from cycles of length represent respectively 4, 5, 6, and 7, and here I presented the case of C5 and C7, where it's required only 1 and 2 doublings. And obviously, if we cut this cycle here and path and put a path of length for n, then we obtained confirmation of our theorem. So for paths, we need to multiply one edge if a path has odd length, and we don't need to multiply any edges otherwise. So for even length path, this is the same coloring as I presented at the beginning of my presentation. And for cycles, if cycles has length equal to 4k, then we don't need to multiply any edges, and this is exactly the same coloring as for C4, which was introduced at the beginning. And for longer cycle, we need to multiply one edge if the cycle has length 4k plus 1, and 2 edges if the cycle has length 4k plus 2 or 4k plus 3. Obviously, k is 1, 2, and so on. On the other hand, for complete graphs of order n greater or equal to 4, we need to multiply 2 edges if a complete graph has has order from 6 to 10, and only one edge should be multiplied otherwise if we would like to find locally equal coloring of such a multigraph. For complete k-partite graphs, which is different from complete graph, we don't need to multiply any edges. So the locally irregular chromatic index of such graph is less or equal to 2. For split graphs, different from complete graphs, it's sufficient that we multiply one edge, and only several graphs need such a multiplication, and one particular family, which consists of clique of order 11 or more, and from one vertex a bunch of neighbors of degree 1. On the our most important result was showing that for power of cycles, okay, power of cycles when the cycles has length n and k is greater or equal to 2, and the graph G is not a complete graph, because then we obviously need some doubled edges. The locally chromatic index of such graph is less or equal to 2. For trees which are not isomorphic to a path of length 1, we need to multiply at most one edge. For unicyclic graphs, except for C3, in which every vertex on the cycle has degree at most 3, we need to multiply at most two edges, and if the cycle has length equal to 3, and obviously the maximum degree of a vertex in such a cycle is at most 3, then it's sufficient to multiply one edge. But this parameter is not bounded. If we consider, for example, a family F star, so the family which is defined analogically than family F, but instead of triangle, we can use arbitrary length, cycle of arbitrary length, and pendant paths could be of arbitrary length, and the distance between cycles over graphs creating such family is arbitrary. Then we need to multiply at most many edges than the number of cycles. So this parameter is not greater than the number of cycles, and among others, such CaRT from family F star required arbitrary many doublings, and also graphs like here require arbitrarily many doubled edges. Obviously, here we show that we require 3 doublings, but if we take such part of a graph and copy it as many times as we want and join here, then we obtain that we need to multiply arbitrarily many edges. And this number of edges could be equal 1/8 of the size of a graph, so quite big. And I think this is all. Thank you for your attention.
Okay, thank you, Igor, for your nice talk. Are there any questions or comments, remarks? No questions?
There's one question.
There is a question, yes, on the chat. Why is needed the hypothesis of degree 10 to the power of 6?
It comes from the proving strategy. It was proved using probabilistic approach, and in such approach, often we can calculate the constant, which is often very big. It comes from the probabilistic method of proving result. In case of deterministic method, we never obtained such big required, for example, minimal or maximal degree.
Yeah. Any other question? It's fine. Thank you. No more questions? Okay, so I think we can say the speakers again. We can thank the speakers again. Thank you for a nice talk. Thank you very much. And now we can go to the last part of our session of today. We have two video talks. The first one is a talk of Eduardo Rivera Campo, entitled a Property of a Plane Convex Set. And the second video talk is a talk of Diana Aveia about telephone numbers. So you feel welcome to watch the recorded talks on our YouTube and Facebook channel.